Uh-huh. Uh-huh. Okay, so the first question, first of all, is dealing with, so here's a quick review. Rules of exponents. So let A and B be real numbers and let N and M be natural numbers. Just, that's what we're going to start with. Then we have the following, we have about 10 rules of exponents, and you probably know a few of them. If you take a to the power n and you multiply with a to the power m, what do we do with exponents? When you have same base exponents, what do? Add them, prime them. That's right. So n plus m, right? And at the same time, if you divide, sure. Yeah, then you, when we divide, what do we do with exponents? Subtract. And finally, when we raise a power to a power, what do we do with exponents? Multiply. So these are the three basic rules that everybody knows, I think, I hope. Otherwise, we're in deeper trouble. Now, there are a few more that you probably know. If you take a product of two numbers or whatever and you raise it to a power, then it is the same as raising a to the power n and b to the power n. So the power kind of distributes. It's not really a distributive property, but the reason for that, because you can write a, b, a, b, a, b, a, b, n times, and you rearrange things. Doesn't work if there's a plus in the middle. Works only with the product, right? If there's a plus, there's a whole new formula, remember, with the squares and rectangles and all that fun stuff. And at the same time, if you take a fraction, two different numbers, raised to the power n, that's the same as raising numerator to the n and denominator to the power n, right? So definitely these five you knew before you met me. Now, the exercises that Eric showed me, or whatever you got on your homework as part of the review, they kind of threw all those rules in the same pile, but they also introduced negative exponents in there, right? Remember those questions on your homework? There are a few problems with negative exponents. So yeah, we are allowed to have negative exponents. Who remembers? What is a negative power? What does it mean? What does it mean to take 4 and raise it to the power negative 2? What does that mean? Does anybody know? Anyone? How many of you did those questions on the homework, the ones that had negative powers? No. Well, okay, so we don't know negative exponents. Yeah, negative exponents mean reciprocals. That just means 1 over 4 squared. That's what negative exponents do. They flip the expression. Now, the reason for that is not just made up kind of a let negative exponents flip things. We don't do that in math. We like to see the reasons for that. So take a look at the property number 2. You subtract exponents, right? Every time you subtract two numbers, there is a chance that the answer comes out negative, right? So for example, if I write something like this, 4 to the power 5 over 4 to the power 7. We understand how to reduce this, right? How would you reduce this fraction? What would that equal to? Anyone, how do we reduce fractions? in the denominator, right? The numerator is 1, denominator is 4 squared, because you just reduce it by 5, right? You subtract exponents. Is that okay? Okay, so we agree that 4 to the power 5 over 4 to the power 7 is 1 over 4 squared. But at the same time, if we use rule number 2, we'll have to subtract exponents. 5 minus 7. 5 minus 7 is negative 2. So these two should equal. 1 over 4 squared is the same as 4 to the negative second power. So negative exponents are reciprocals. That's what they do. So every time you see a negative exponent, in order to turn it back into a positive exponent, you just take the reciprocal. So a to the negative n is 1 over a to the n. Or in the bigger picture, if you take a fraction and you raise it to a negative power, all that negative sign does is takes the reciprocal of your fraction, so it becomes b over a to the power n, like that. So these are the two rules that, well, you should have seen before, but anyway, so now they're official, okay? So when you deal with questions like you saw in the homework from section 5.3 maybe, one of the goals is to have no negative exponents in the final answer. How you get to that, there's no, do this first, do this second. You just kind of use the order of operation, operate with these rules. We shall be able to arrive to the same answer, taking different routes. So let me try, what was that question, Eric? All right, so you have a numerator, 2x to the power 9, y to the power negative 3 over 5, x to the negative 4th power, and y to the power 3, and everything raised to the power negative 3. So it's a big mess, okay? Yeah. Again, there's no do this first, do this second, do this third type of process. You kind of have a freedom of choice. What do you want to do first? Here are your options. You can just get rid of the outside negative power by flipping the whole fraction, right? The rule number 7. If you have a fraction raised to negative power, just flip it, get rid of negative power. You can do that. You can do this. You have x on top, x on the bottom. So you're dividing. You can use rule number 2 to combine those. You have y in the numerator, y in the denominator. So we're dividing, right? Y by y. We can use rule number 2 to combine that. And then deal with the negative on the outside. So there's no, again, there's no exactly follow these types of steps. Just don't invent your rules. That's usually what gets you in trouble. But operating with the whatever 7 rules I have, we should be able to get it done. So for whatever reason, because it's Monday, I'm going to get rid of the negative on the outside first. You don't have to do that first. But hey, I feel like doing that first. Is that okay? So I'm just going to flip the inside fraction. I don't have to do that, but 5x to the negative 4th power y cubed over 2x to the 9th and y to the negative 3rd power. Everything cubed like that. So you see, all I did, I changed the sign of the outer exponent by flipping the inside fraction entirely. Yeah. Well, because that negative. If I didn't have that negative, if I kept the outside negative, then yes, I'll have to change all the signs on the inside. But I'm just following the rule number 7 that tells me if you want to lose the negative exponent, then just flip a fraction. I'm not making any other changes. Okay? Now I can start dealing with this, because look what I can do. So 5 halves is 5 halves. Who cares? I'm not going to mess with 5 halves yet. So now I'm looking at the x's, right? So I have x to the negative 4th power over x to the 9th power, right? So one way to do that is to say, well, I'm dividing, right? Same base, different exponent. Rule number 2 tells me to subtract exponent. So that will give me x to the negative 4th power minus 9. Right? I'm just subtracting. Negative 4 minus 9. Right? And I can do the same. What? I can do the same thing with the y's. Following the rule number 2, I will subtract exponents. So it's y cubed minus negative 3. I still have a big 3 on the outside. Right? So still 5 halves. Negative 4 minus 9 is x to the power negative 13. 3 minus negative 3 gives me positive 6 cubed. Right, just performing those operations. Right? Is that okay? Okay. Again, I could have done this first and then deal with the negative, but, you know. All right, so let's cube this whole thing. Now remember, the cube will cube a fraction. It'll become 5 cubed, 2 cubed. Okay, so it will literally take a fraction and cube it. Now with exponents, what happens with exponents when you raise power to a power? You multiply. So we need to multiply negative 13 by 3 to get negative 39. Right? You multiply negative 13 times 3. And we have to multiply 6 and 3. So that's y to the power 18. Is that okay? What? So what was that? No, there was always a product here, right? And if there was a plus, then I'm in a whole different world of pain. I cannot just distribute through a plus. I mean, I have to FOIL it 3 times if I cube something. There's a formula that allows you to cube faster. It will give you 4 terms. So, but with the product, I can do that with the product. Anywho, that's not my final answer, because we don't like leaving negative exponents in our answer. So all it means, if I have a negative exponent, it's just going to go in the denominator. That's all it means. Or negative exponents, they just change the level of a fraction that they live on. If you have a negative exponent in the numerator, it becomes positive exponent in the denominator. If you have a negative exponent in the denominator, it becomes positive exponent in the numerator. You can always do that. I mean, we could have done it right off the bat. X to the negative 4th power in the denominator becomes x to the 4th power in the numerator, x to the power 13. Negative power in the numerator goes as a positive in the denominator. So it's y to the power 6 cubed plus another cube. So we will still get the same results. But anyways, so all I have to do is to, well, 5 cubed is 125. Y to the power 18 stays on the top. Over 2 cubed is 8. Right? And x to the negative 39 becomes x to the positive 39 in the denominator. This is not the only way to do this problem. You can do similar steps almost in reverse. You still should be able to get the right answer. Basically, yeah. You just don't put it, because I still have stuff in the numerator, so no reason to put a 1. Because again, those are all products. So you should still be able to arrive at this answer by not following these steps precisely. Well, I mean, let me show you an alternative way. Don't write this down, but alternatively, I was just saying negative exponents. Where's my magic pen? Negative exponents from the denominator go in the numerator. Negative exponents from the numerator go in the denominator. If I just do that right off the bat, I'll have 2/5 x to the 9th times x to the 4th over y cubed times y cubed. So the negative exponents change the level and change the sign. Right? So negative 4 in the denominator became positive 4 in the numerator. Negative 3 in the numerator became positive 3 in the denominator. I still have negative 3 on the outside, right? Well, because I mean I had this x, and I moved that x on top. So I have x to the 9th and x to the... I'll combine them in a minute. I'll still get x to the power 13. I'll still get, because you add exponents, right? Y to the power 6. Right? You still add exponents. What is the negative on the outside going to do? Flip the fraction, so that becomes 5x to the 13th over... I'm sorry, no. Be more careful. Five y to the 6th over 2x to the 13th power positive cube. And then if you cube everything, you'll still get the right answer. Maybe this is even quicker. Right? I mean, right, you have 5 cubed is 125. Power 6 cubed is power 18. 2 cubed is 8. 13 times 3 is 39. So you still get the same answer. So again, there are ways you can do that. Just keep in mind, negative exponent just changes the level where the number leaves or whatever. Okay? What was that other one? So 5a negative 3b negative 4, 2a negative 4b, so that's 1. And the other one is x squared minus 24 25th plus 2/5 x. What are we supposed to do with that one? Well, the question is factor. Okay. Okay, so this one. I mean, the parentheses here just to mess with you. You don't need them. They're just a big product. You're just multiplying everything. Right? That's a big product. So the way you multiply things, you can multiply 5 and a 2, right? So that's 10. Now what do you do when you multiply x, a to the power negative 3, and a to the power negative 4? What do you do with exponents? Add them. So negative 3 plus negative 4 gives you what? Negative 7. So it's a to the power negative 7. And same thing with the b's. You have b to the negative 4, and then b to the positive 1. So that gives you what? Negative 3, right? You just add exponents. Well, negative exponents go in the denominator. That's basically it. 10 states, a to the 7th, b cubed. So negative exponents, they change the level. They go from numerator to denominator and vice versa. Now this one is going to be a little more interesting. Okay. So if I try to factor this, and this is, okay, that's a plus. Let's just write it like this. Right? Is that okay? Just rearrange them, make it in the order that we like a little better. Did your quiz work out? Did you get my email? Yeah, you can still redo. Because like on my end, it was like, you never even touched it. Yeah, it didn't even say anything like that. So how do we factor trinomials that do not have a coefficient in front? What is the theory there? Ignore the fractions. Let's pretend the numbers are pretty. What do you have to do? What is the process? What are you looking for? I mean, if I give you a nice problem, x squared minus x minus 12, how would you factor that? What are we looking for? No. Well, yes, but there is none, right? So, yeah, the first thing you look for is the greatest common factor. There is none. So how do we deal with a trinomial that does not have a coefficient? based on what we did last week. You were telling me what to do last week. Where is Nick? He was helping me a lot. So where do those numbers come from? What were you doing? Right, so this is the product, and this is the sum, right? So you need two numbers that multiply to negative 12 and add to negative 1. So we need numbers that multiply to negative 12 and add to negative 1. So yeah, those numbers are negative 4 and positive 3. So then you automatically go x minus 4, x plus 3. And we're done. Right? Most of you were here last week. Why the blank stare? I mean, does that look okay? I mean, we spent a lot of time on that. So apply the same idea here. Two numbers that multiply, this is kind of fun. Two numbers that multiply negative 24 25th and add to positive 2/5. Okay? This is a little sneaky, but let's think about this. If two numbers add to the positive 2/5, they both have to have 5 in the denominator. Do you agree with that? There's only way two numbers add to something with a 5 in the denominator if they have 5s in the denominator, right? And two numbers that have 5s in the denominator will multiply to a number that has 25 in the denominator, right? So we know at least that both numbers will have to have 5s in the denominator. So we need two numbers that multiply to negative 24 25th and add to 2/5. So we know right away one number is over 5 and the other one is over 5. There's no other way that can happen, right? There's no way they can multiply to something over 25 and add to something over 5. So the only hang up is the numerator. Well, what two numbers multiply to negative 24 and add to positive 2? What? Well, they'll multiply to 20. 6 and what? How are the signs? Yes, so positive 6, negative 4. These two numbers will multiply to negative 24 25th and will add to positive 2/5, right? So the denominator was not even an issue. The second you recognize that they both have to be 5th, then we're good. So then the factoring of that problem is just going to be x plus 6/5, x minus 4/5. It is tricky, but the denominator was not that big of a problem. If they put some weird denominators, then it'll be harder. But 5 and 25, there's only way that can happen. So it's not even a problem. Is that okay? Okay. Good. Well, this is fun. Factoring is important, so we will definitely take our time on that. So okay, so last time we started that formulas of quick multiplications. So we did have the difference of squares. So that's the difference of squares. And we had two more, the perfect square trinomials. We put down a plus b squared equals a squared minus 2ab plus b squared, I'm sorry, plus 2ab. And a minus b squared is a squared minus 2ab plus b squared. Right? So we We introduced those formulas last time, so a big chunk of this worksheet that that worksheet 4 or whatever, was using those formulas. So the first one is called square of a sum. The second one is called square of a difference. So these ones you need to know. I mean, there's no way to get through any of those math courses without knowing these three formulas. These are must know. There are some cubic formulas. They'll help you to factor things fast and multiply things fast. So the two factoring formulas that use cubics are the formula for the sum of cubes and we'll have a formula for the difference of cubes. So that's sum of cubes, difference of cubes. Now, I'll give you those formulas on the test. You'll have them written on a front page, whatever. You don't have to have them memorized because they're a little messy. But you need to know that they exist and you need to know how to use them, given when you see them in front of you. So the first formula for the sum of cubes is a plus b, and then a squared minus ab plus b squared. This is how you factor the sum of cubes. Now the difference of cubes, it's very similar. The first parenthesis will have a negative, while the second parenthesis just entirely positive. When factoring using the sum of cubes formula, you're always going to end up with a quadratic trinomial looking like that. That is impossible to factor. It's never factorable. Okay? It's very close to our square of a sum formulas. It's just missing a 2, right? The difference between these two formulas and those two trinomials here is just the missing 2 in the middle. That's what prevents it from being factorable. Sometimes those trinomials are referred to as degenerate quadratics. Not making this up. Some books call them that because they didn't get that 2 in the middle for whatever reason. So that is whatever's left here we cannot factor. Okay? Now, just to quickly show you that these formulas are in fact working. I mean, if I tell you that this factors into that, how can you check? How can you always check your factoring problems? Yeah, just FOIL them out. So in theory, if I take, don't write this down, but if I take a plus b and a squared minus ab plus b squared, and I FOIL this out, I should get a cubed plus b cubed. Right? That's the idea. That's how you know well that's correct. So if I do that, a times a squared is a cubed. A times negative ab is negative a squared b. A times b squared is positive ab squared. Right? And then you multiply by b. B times a squared is positive a squared b. B times negative ab is negative ab squared. And then positive b times b squared is positive b cubed. If you just do that FOIL. I mean, if you call it FOIL, it's something else, but same concept. So is anything going to cancel? Yeah, a squared b, ab squared, ab squared. And we're left with a cubed plus b cubed. And the same thing works if you FOIL the second formula. So, I mean, I'm not going to do that. Okay? I'm just going to show you how to use it. So let's say the example is to factor something like this. A factor, let's say, x cubed plus 8. Here's a very nice example. X cubed plus 8. So, no greatest common factor, not a quadratic, so we start freak out. But what you notice is that x cubed is a perfect cube, right? And so is 8. Is 8 a perfect cube? What is cubed? What cubed equals 8? 2, right? So really, you don't need to write this step down, but this problem is x cubed plus 2 cubed. That's what really is going on here. Figure that? And 8 is a perfect cube. So all I have to do now is to just match this with my formula. What is A in my formula right now? And what is B? 2. So that means for every A, I have to put an X, and for every B, I have to put a 2. So then it just automatically, I don't have to really do anything else. It's X plus 2, A plus B, and then X squared plus AB, so that's 2, I'm sorry, minus, right? There's a minus in here. X squared minus 2x plus B squared, which is 4. Just using that formula right there. For every A, you put an X. For every B, you put a 2. How's that? Is that okay? And now, even if you try, and this is what I was saying earlier, even if you try to factor x squared minus 2x plus 4, you need two numbers that multiply to positive 4 and add to negative 2. And, you can try and try and try. You won't find that combination. Okay? Those are not, they're not even real. I mean, those numbers are weird. They're spooky or whatever. So we're done. There's nothing else you can do with that. That's as far as we can go in that example. Well, it's just kind of to help for you to see that 8 is in fact 2 cubed. So we see which number is being cubed here. So, because a very common mistake with these problems is to treat B as 8, just without ignoring that. It's still something cubed. You just take plugging 8 for every B, and then you get something ridiculously huge. So just think about which number cubed is 8, or whatever that thing is. Let me do another one. 27x cubed minus y cubed. So that looks like we're subtracting 2 cubics. And so that's a difference of cube type of situation. Now, without me writing that extra step in the box, can you tell me what is A for this problem? What is the value of A? What is cubed in the first place? What? What about the, it's 27 cubed? So what is cubed here? What is the role of A right now? What am I going to be plugging for every A? 3 and x, right? That's a 3x cubed. Because this is what I was doing here. It's always easier for us to see if you rewrite it as something cubed minus something cubed. Then you can see that 3x is A for the purposes of our formula. Right? What? Yeah, because again, this is something cubed. Well, 3 cubed is 27. Right? Because again, this formula says it has to have a quantity that is cubed. There's nothing in front of A cubed. So you have to also treat 27 as a part of a quantity that is being cubed. So, well, the quantity, that's 3x. So 3x is going to play the role of A. So if I plug it into my formula, I'll get 3x minus y. And then I'll have to square 3x to get 9x squared plus their product, 3xy plus y squared. And again, if you start foiling this, we'll see what happens. When you multiply 3x by 9x squared, you get 27x cubed. This is why we have to break 27 as well. You have to break the entire quantity down to the base that is being cubed. Does that make sense? Because if you keep it as 27, your numbers will get huge. Is that okay? Question? How about this one? X cubed minus y to the power 6. Can we break that one down? Again, I'll just copy these formulas here so we can see them. I know they're in your notes, but it'll be easier for me to refer to them. So tell me, what is going to play the role of A and what is going to play the role of B in that formula? What is A right now? That's a 3 here. Yeah, so just X. What is B? Just Y? Because again, B is whatever's cubed. What is cubed over here? Y squared. So we have to cube y squared to get to y to the 6. So again, that step that you don't need to write, you think of this as 2 cubes. X is A and y squared is B. Is that okay? So then, when you recognize A and B, the rest should be simple. X minus y squared, right? A minus B. And then A squared plus their product plus the last term squared, which is y to the power 4. Right? When you're asked to factor, what it means, you always want to go as far as you can. When you think that you're done factoring, you should ask yourself, well, can I factor any further? All factoring questions are really factor completely, not just start factoring. You have to get it all the way down to the product of simplest terms possible. So this is why it is important to analyze each factor that you think you have in your answer. Here, none of those can be factored any further, but it's always a good habit to check your factors to see whether they can be broken down any further. Having said that, try to factor something like this. X to the power 4 minus 16. I'm not, okay, anyways, so here we go. Trying to factor complete. So I have to develop a certain strategy to do that one. Because the first thing is just no matter what, look for the greatest common factor. So that's not, doesn't have it here. So then try to think, well, I mean, is there any of our fancy formulas that can be applicable here? What is this formula? I mean, this expression, x to the 4th minus 16, does it match? Or does it at least look like any of our formulas? What? Number 5? Well, but my power is 4, right? I have x to the power 4. This is cubed. It's hard for me to think of a power 4 as something cubed, right? 4 is not a multiple of cube, but 4 is a multiple of 2, right? I can think of the 4th power as something squared. Can I think of this expression as a difference of 2 squares? X to the power 4 minus 16. I mean, we can think, can be thought, I guess that's how you spell thought, of as a difference of squares. Because x to the power 4 is a perfect square. What is squared gives you x to the power 4? Yeah, x squared squared, x to the power 4. How about 16? Is 16 a perfect square? Yeah. So using the difference of squares formula, I can write it as x squared minus 4, x squared plus 4. Just using the difference of squares, right? Whatever squared gives you x to the 4th, whatever squared gives you 16. Are we done? No, why not? What else can I do? Well, you went like that, so you knew what's going on. Or you're using your advanced skills of pattern recognition. Well, what did I just say? That when you think you're done factoring, you should always look for, is there a way to factor it even further? Is there a way to factor this thing even further? Is there any one of those things that are factorable, x squared minus 4, x squared plus 4? What can I break down? 4. You just gave me a number. Well, what does that mean? And what are you trying to break down? That one. The difference of squares, right? It's x squared minus 4. We have a formula for that, right? We don't have a formula for the plus, so the only thing we can break down further is the x squared minus 4 will become x minus 2x plus 2. X squared plus 4 stays. We cannot break down a sum of squares. So now this is factored completely. We cannot go any further. Does that make sense? What? I mean, kind of. If I just, without the first one, if I just gave you, can you factor that? You're like, all right, well, difference of squares. Why not? I can break that one down further. Right? Well, this is fun. How about this one? The tricky thing about this problem is that it can either be thought of as a difference of 2 cubes, because you can always think of power 6 as something cubed. Do you agree with that? I can think of this as a difference of 2 cubes, because it's x squared cubed, y squared cubed. Or I can think of this as a difference of 2 squares. Every time you have even exponents, you can always think of an even power as a square. Do you agree with that? Oh, yeah, yeah. So if I had, but if I had something like this, then I can only do this as a difference of squares because 16 is not multiple of 3. But any power that's multiple of 3 is a cube because we multiply exponents. Every power that's even is really a perfect square because we, multiply exponents. So when facing this situation, and this is kind of almost a rule, if you have options, either think of this as a difference of cubes or a difference of squares, always start with difference of squares because that's an easier formula. Okay? So starting with the difference of squares, how would you break that down? Just using the difference of squares. What are the things that are squared in there? No. Cubed. Because what is squared to get power 6? The cubics. Because I think of this problem as y cubed squared and x cubed squared. These are my differences of squares. So what are the bases? The x cubed. Whoever said that, good. X cubed plus y cubed, x cubed minus y cubed. right? They're just breaking it down using the difference of squares formula. Is that okay? Can I go any further? Yeah, because you're just looking at a sum of two cubes and a difference of two cubes, right? X cubed plus y cubed is just sum of two cubes. We have a formula for that. We'll just use that formula straight up. Replace every a with an x. Replace every b with a y. So that was the sum of cubes. And the difference of cubes, just again, using the formula without really thinking much. I'm just replacing a's and b's with x's and y's. That's about it. So again, I'm just looking at this, right? And I'm just comparing it with that, right? X cubed, y cubed, a cubed, b cubed. So I just need to replace, every a with an x and every b with a y, and I'm done. This formula does all the work for me. Yeah, so the cube is being broken down in there. And same thing here. I'm just matching it perfectly. I mean, there's nothing to think about. You're just rewriting the formula. Otherwise, it's hard. It's hard to factor cubics, but it's easy when you're using those formulas. Right? I'm just replacing every a with an x and every b with a y because they're just simple x cubed, y cubed situation. Does that make sense? Does that make sense? Are you sure? Positive? All right. Well, then let me put you to work now.